In this lecture, we'll start looking at finite volume methods for nonlinear systems of equations and see how to extend the wave propagation methods for systems of equations, and in particular, how to define high-resolution methods that use wave limiters and what we have to do differently when these waves are not all simply proportional to the same set of eigenvectors, but are vectors that have to be limited in phase space. And then we'll look at an example for the shallow water equations. So again, just reviewing the basic idea of Godunov's method. In terms of the wave propagation form, we can look at solving the Riemann problems at each of these interfaces, and then rather than trying to compute the average at the end of the time step or the fluxes at the interfaces, instead, what we'll do is update the cell averages based on the contributions from all the waves that are entering each cell from either the left or the right edge. And by doing it this way, we can add in higher order correction terms using limiters. So in order to do this, we need some way to define what we mean by the waves coming out of a single Riemann problem. And from the form that we were looking at here on this slide, the waves, I'm assuming, are jump discontinuities propagating with some speeds s for each wave. And whereas we know in general for nonlinear problem, we could have rarefaction waves as well as shock waves. And so we need to first figure out a way to sort of write things in terms of a wave decomposition. So for a scalar equation, we saw that, of course, for scalar advection, there's always just one wave, which is the jump in q moving at a speed that's given by the advection velocity. But for a scalar nonlinear problem, we could use the same formula, but with the shock speed given by the Rankine-Hugoniot condition, just the jump in f divided by the jump in q. And we saw that in the case of a scalar equation, at least, that was actually exact. If the true Riemann solution consists of a shock wave, that is the shock speed. And it could be used also in the case of rarefaction waves. And once we do the averaging of Godunov's method and onto the next time step, it's actually also exact for Godunov's method, except in the case of transonic rarefaction wave, where we had to put in some sort of an entropy fix. And again, for nonlinear systems, we'll also see that in the case of transonic rarefactions, we need to do something a little special to put in a transonic rarefaction entropy fix. But I won't go into that in this lecture. Here we'll look at something that's more like a generalization of the approximate Riemann solver for the scalar case, where we just replace rarefaction waves with the shock wave, for example. And for the scalar nonlinear problem, we could also look at applying limiters in terms of wave limiters. And we wrote the wave propagation method first as Godunov's method, where we just update the cell averages based on the waves. But then we also looked at the Lax-Wendroff type method for a scalar nonlinear problem, where in addition to the updates based on these fluctuations from the first order Godunov method, we also defined some correction fluxes, these f tildes, and used a flux differencing form to add in the second order correction term. And if we just want to do a Lax-Wendroff type method, then you can define this correction flux as a natural generalization of what's done for the scalar advection equation, where it's now the absolute value of the speed that comes in here. And the full wave strength, the full jump in q, is used in these correction terms for a Lax-Wendroff type method. The problem, of course, with Lax-Wendroff, although it's formally second order accurate as we refine the grid, if we have steep gradients or discontinuities, it tends to give oscillations. It's a dispersive method, and so we introduce the idea of wave limiters for high resolution methods, where we basically use exactly the same algorithm, except that in place of the full wave strength, we use a modified wave strength W tilde, which is gotten by taking the full wave strength and multiplying by phi of theta, where phi is some limiter function, the min-mod function, monotonize centered, or some other limiter, and the theta is the ratio of the wave looking on the upwind side to the wave that we're trying to limit. So this capital I is either little I plus 1 or little I minus 1, depending on whether the speed is positive or negative. But in the scalar case, the wave is simply a scalar jumping Q, and so we can just look at this ratio of scalars as our definition of the smoothness indicator theta, and then we apply a limiter to that, just as we developed originally for the scalar advection equation, and that tells us how to limit the W tilde wave. Now, if we want to extend this to a system of equations, well, if it's a constant coefficient linear system anyway, it's relatively simple, and there's a couple of different approaches you could use. For a constant coefficient linear system, we could simply diagonalize the system, and if we do that, then that allows us to write it as a decoupled system of linear advection equations, where the eigenvalues lambda on the diagonal of this capital lambda matrix are the advection velocities for each characteristic variable, and the characteristic variables can be defined as in terms of the matrix R of right eigenvectors. So we could diagonalize the system, we could apply the scalar algorithm to each component separately, solve the equation to whatever time we want, or in each time step we could decompose into characteristic variables, apply a scalar algorithm to each component, and then compute Qn plus 1 by recombining using the eigenvectors. But another way to do it, which is completely equivalent for the constant coefficient linear case, is to solve the Riemann problem and decompose the jumping Q into waves, where the waves are each proportional to one of the eigenvectors. So we'd be applying the inverse of the eigenvector matrix to the jumping Q to get the alphas. And then these alphas are simply scalar values, and so we can apply a wave limiter to each of those scalars and then recombine them. And if we do that, that turns out to be exactly equivalent to diagonalizing the system, applying the same limiter high resolution method to each scalar equation and then recombining them. But the second approach generalizes more easily to nonlinear problems, or even for that matter, variable coefficient linear problems where the eigenvectors vary. You can't simply diagonalize the system altogether, but you can still do a sort of a local diagonalization at the solution of each Riemann problem. And in the nonlinear case, we can solve the Riemann problem in terms of waves, and so we can generalize the approach this way. But again, we'll have to apply the limiter somehow to the waves rather than to the original variables. And now in the case where it's not a constant coefficient system, those waves are going to be vectors that aren't necessarily collinear. So we have to do a little more work to understand how to do that. But here is the basic idea of the wave propagation algorithm. Again, the first terms here where we just add up the contribution of each wave to each cell average, we're multiplying by the speed. Well, for the waves coming from the left edge, we're multiplying by the positive part of the speed, so we're only picking up the right-going waves at the left edge, and then at the right edge of the cell, we're multiplying by the negative part of the speed, so we're only picking up the left-going waves from the right edge of the cell. And this top line here is just Godunov's method applied in wave propagation form, and then we add in this flux differencing form of the correction fluxes, where the correction fluxes look exactly as they did before, with some limited version WP tilde of the wave in order to avoid oscillations. So in order to apply that, as I said, we need to determine how we're going to split up the Riemann problem into a set of waves that are simply discontinuities propagating at constant speed, so that we can apply the approach of the previous slide. So there's a whole theory of approximate Riemann solvers for nonlinear systems. And in the next lecture, I'll talk more about some of these approaches to approximate Riemann solvers. But one simple approach that you might consider is if we know how to solve the Riemann problem, say for the shallow water equations, we know how to find the exact Riemann solution by using both integral curves, which are used where there are rarefaction waves, and shock Hugonio loci where there are shock waves. But if we ignore the possibility of rarefaction waves and simply use the Hugonio loci, then we can construct a weak solution that consists entirely of discontinuities propagating at speeds given by the Rankine-Hugonio conditions. It might not be the physically correct vanishing viscosity solution, because maybe some of those discontinuities should be rarefaction waves, but it gives a way of doing the solution that we could use in the wave propagation algorithm. But a disadvantage of that is that even just finding the intersection of these Hugonio loci requires solving a nonlinear equation. In the case of shallow water equations, you can solve that analytically, but for other systems, you may have to use some nonlinear solver in order to find the intermediate states. So it's still expensive, and it's not really necessary to do all that work. Sometimes we can use much simpler approximations sometimes. So one very simple approximation is to simply always use two waves with speeds that sort of approximate the minimum and maximum characteristic speeds around this Riemann problem, and then choose a single intermediate state in between them. And as we'll see in the next lecture, there's a sort of unique way to do that so that the resulting method is conservative. Or another sort of more sophisticated way that's intermediate between these is to do some sort of local linearization, where depending on the data of the particular Riemann problem we're looking at, depending on Q left and Q right, the value in the state in the cell to the left and to the right of the interface, we define some approximate Jacobian matrix called A hat based on that data, and then compute the eigenvalues and eigenvectors of that matrix and solve a linear system where we know that the waves can be written in terms of the eigenvectors. Of course, you want to do that in a way that those eigenvalues and eigenvectors are much cheaper to compute than the full Riemann solution, so there should be analytical formulations for that. You also want to ensure that once you've done that, the resulting method is again conservative, since we know we need to use conservative methods in order to converge to the appropriate weak solutions. So in the next lecture, we'll look at something called the row solver, which is one particular way of sort of choosing this approximate Jacobian that has some nice properties. But for now, let's just suppose we have some way of splitting up for any left and right states. We have a way of generating a set of waves, which are jumps in the solution, propagating at corresponding speeds. That gives a conservative Godunov type method. And now let's look at the question of how would we apply limiters to those waves. So once we've split the jump in Q up into waves, however we want to do that, and however many waves we have. So I've written it here in the case of when we do a decomposition into a linear system, or the approximate Riemann solver where we approximate the Jacobian matrix, then our waves would be linear multiples of some set of eigenvectors. And for a constant coefficient linear system, those eigenvectors would be constant vectors. They wouldn't vary. And it's only the scalar, the coefficient alpha p, that varies from one Riemann problem to the next. And so then we want this W tilde to be some limiter. I think I used lowercase phi before, but some limiter phi of theta times the wave. And now, because each of the waves is a scalar multiple of the same eigenvector everywhere, we can just define a smoothness indicator theta by looking at the ratio of the scalar alpha coefficients, again looking in the upwind direction based on the speed of this particular wave, looking at the alpha coming from the Riemann problem at capital I minus a half, and comparing that with the alpha at the Riemann problem little I minus a half that we're trying to limit. And in the scalar case, this would simply reduce to looking at the ratio of the jump in Q at the upwind interface to the jump in Q at this interface. But for a constant coefficient linear system in general, we can apply exactly the same sort of limiter method, just using the scalar coefficient alpha as in our smoothness indicator theta. But for a more general system, if we split the jump in Q minus Qi minus 1 into some set of waves, which might not even be the same number of waves as the number of equations in the system if we're using this Harton-Lax-Van Leer method, for example. So we just have some set of waves propagating with some speeds. We want to do the same sort of thing. We want to look in the upwind direction. So capital I will be the neighboring Riemann problem in the upwind direction for the pth wave. And then we want to compare the wave that we're trying to limit with the wave from that upwind Riemann problem. But now these waves are vectors, and so we need to somehow reduce this comparison to comparing two scalars so that we can define, again, a smoothness indicator theta that should, as in the scalar case or the linear system case, we'll apply a limiter that has phi of theta equal to 1 for theta equal to 1, so that it compares with the second order methods well there. And so this scalar should be close to 1 where the solution is smooth. But we don't want to just use, for example, the magnitude of the waves, which might be one way to measure whether the solution is smooth or not, because the waves might be pointing in very different directions in phase space. And we know from the scalar problem that we also want to choose our smoothness indicator in a way that it's negative near extreme points, because our limiter function phi of theta then reduces to phi equals 0, where theta is negative, which means it flattens out the extreme points, but it completely avoids non-physical oscillations arising, at least in the scalar case. So given these two vectors in phase space, we want to define a scalar theta that is comparable, or that allows us to compare these two waves in the same way that looking at the alphas did in the linear system case, or just looking at the jumps in Q does in the scalar case. So one approach that works quite well in general, and is the approach that's built into clawback, is to take the projection of the wave W capital I minus a half from the neighboring Riemann problem, take that vector and project it onto the vector that we're trying to limit. And so if you can sketch a picture here, if this is, say, the wave that we're trying to limit in phase space, and the neighboring wave at interface capital I minus a half is this vector, then we would project that vector onto the wave we're trying to limit, and the coefficient here is exactly the multiple of the original vector that we have to take. So here might be 1/2, for example, so that this projection is maybe 1/2 the total length. And this has a nice property that if you have a vector which points in a totally different direction, then its projection onto this vector might actually be a negative multiple of the original vector. And so when there's this sort of difference between the wave we're trying to limit and the neighboring wave, then we would end up with a negative value of theta, and that would cause the limiter to cancel out the higher order correction term in that case and reduce basically back to the Godunov method, which is what we want to do to avoid oscillations in general. So we'll define this theta to be exactly this scalar coefficient, which is the inner product of Wi minus a half with W capital I minus a half divided by the inner product of Wi minus a half with itself. That's the appropriate scalar here when you compute the projection. And then again, we'll replace the wave we're trying to limit with this WP tilde, which we get by applying some limiter function to this theta, and then scaling the wave by that. And again, the same set of limiters that we talked about originally for scalar advection can be used here. If we're looking at an approximate Riemann solver that sort of decomposes the jump in Q into a linear combination of eigenvectors, either of a constant coefficient linear system or maybe of an approximate Jacobian in the nonlinear case, then we would use exactly the same approach. But in the case where we have a constant coefficient linear system, then these eigenvectors would be constants. They'd all be equal. And so when you calculate this, you'd find that it reduces to simply the ratio of the coefficients of the eigenvectors in our eigendecomposition in that special case where we have a constant coefficient system. But again, it generalizes it to non-constant coefficient linear systems and also to nonlinear problems. Oh, and also in the scalar case, this again just reduces to being the ratio of the jump in Q from the neighboring Riemann problem to the jump in Q that we're trying to limit. So let's look at an example for the shallow water equations. So here I've drawn the phase plane, the HU plane for the shallow water equations, which we've seen before. And I've drawn the Hugonio loci, which are the curves that connect two states that satisfy the Rankine-Hugonio condition. So these are states that can be connected with a discontinuity propagating at some speed s. And notice that the speed s is always just between any 2 points that are connected by a Hugonio locus. The corresponding shock speed s is just the jump in HU divided by the jump in h, since the first equation in the Rankine-Hugonio system says that the jump in the flux HU has to be equal to s times the jump in h. So the slopes of these curves give us, or not the slopes of the curves, but the slope of the tangent line between any two states along one of these curves tells us the speed at which that discontinuity is propagating. So I've drawn a few states here, assuming that we're solving a problem where we have a number of different states, and we want to look in particular at the interface between states qi minus 1 and qi. That's where we've defined the waves wi minus a half that we want to apply a limiter to. So in this case, since the blue curves are the one waves and the red curves are the two waves, from qi minus 1 we would move to some other point that lies on a blue curve to give us a one wave, and then from there to some other state qi that lies along the red curve, giving us a two wave. So the intersection of those two curves tells us what the intermediate state is between qi minus 1 and qi. And in this case, the slope of the line connecting this intermediate point with qi minus 1 is negative, so we have a one wave that's moving to the left in the xt plane, and the other slope of the between qi and the intermediate state is positive, so we have a two wave that's moving to the right. So that's sort of the classical picture where we have shallow water equations, and in this case our intermediate state qi minus a half in the xt plane is there, or in the phase plane is this point qi minus a half. So now to apply limiters to the waves, the jump between qi minus a half and qi, for example, tells us the two wave, the wave that's moving to the right. Let's look at that wave first. So we'll look at the wave which joins this intermediate state to qi, and that would be the wave that we would call W2 at I minus a half. And to apply a limiter to that, we want to look at the corresponding wave in the Riemann problem that's one cell to the right on the upwind side, since this has a positive, to the left, since this has a positive wave speed, then the Riemann problem on the upwind side would be the one to the left. So from qi minus 1, we'll look at the state qi minus 2, which is the next cell to the left, and we'll solve the Riemann problem there, which will give us these two waves. And now the wave that we want to compare our W2 with is the two wave coming out of that, so that's this wave here. This wave here is W2 at capital I minus a half, where capital I is I minus 1 in this case. And so to limit this wave that we're trying to limit, we would look at this corresponding wave from the upwind side. Now in this case, the two look like they're pretty much collinear, so the projection of this shorter wave from the upwind side onto the wave that we're trying to limit might look like this, for example. And so the fraction of the original wave that covers would be the value theta. In this case, it looks like it might be, I don't know, 2/3 or something. And then we would apply our limiter phi to that value in order to figure out how to limit the W2 wave. And if we were using something like min mod, then we would use the smaller, basically, of 1 and that coefficient, 2/3, say. And so our limited wave would actually be the shorter wave, W2 tilde, if we were using min mod, for example. If we're using a different limiter, it might be different from that. But that would be how we would limit things. And if the data is sort of smoothly varying, then we would expect these waves to be quite close to each other. If all the states lie very close and the jump between qi minus 1 and qi is comparable to the jump between qi minus 2 and qi minus 1, then the sort of change in eigendirection from one state to the next doesn't vary much. And this, in the limiting case, as we have very smooth data, would basically apply to the same, or reduce to the same thing we use for the linear system. Okay, but now let's look at the same problem, but how we would limit the one wave. So we've started again from qi minus 1. We've got a one wave which goes to the intermediate state. So this is our one wave that we're trying to limit now. And so that is moving to the left. That's our left-going wave. And so in this case, we want to compare that with the W1 wave that comes out of the Riemann solution between qi and qi plus 1. And the Riemann solution there that we're using would go from qi along the blue curve to this intermediate state and then to qi plus 1. So the W1 wave that we'll be comparing to is this wave here. And now you can see that these waves point in nearly opposite directions in this case. And so when we project W1 at I plus 1/2 onto W1 at I minus 1/2, we'll get something that's negative. And or the coefficient multiplying W1 will be negative. The projection might look like this, for example. And so we'd be applying a limiter to a negative value, and all of the limiters we looked at, the TBD limiters, would always return 0. And so in this case, our W1 tilde would just be the 0 vector. Okay, so just very briefly to summarize, what we need to apply the wave propagation method for a general system, linear or nonlinear, is a way to split up the jumping Q at each Riemann problem as a set of discontinuities that are propagating at some speeds. And then we can use those waves directly to update the neighboring cell averages. That's just Godunov's method, or an approximation to it anyway, depending on what approximate Riemann solver we use. But then those waves we can also think of as giving us a decomposition of the slopes. So another way to think about this is that if we look at the derivative of q with respect to x, that's approximately the jump in q divided by delta x, and the splitting of the jump in q is a splitting of the slopes, and then we can use those together with limiters, applying a limiter to each one of these waves as a way to add in the second order correction terms that, in the case of smooth flow, would give us something close to second order accuracy. So in the next lecture, we'll look more at how we can actually approximate the Riemann solution with a cheaper but accurate approximate Riemann solver.